Good morning, everybody. My name is Karl Vilacoba, and I am the Communications Director for the Monmouth University Urban Coast Institute on the Jersey Shore, and a member of the Mid-Atlantic Ocean Data Portal team. Last month, we published our first series of map layers on the portal showing standard sea surface currents for each season in the Mid-Atlantic and southern New England waters. These maps were the latest products developed through a partnership between the Mid-Atlantic Regional Association Coastal Ocean Observing System, or MARACOOS, the Mid-Atlantic Regional Council on the Ocean, MARCO, and the portal team. Through this partnership, we're working to create map products at a scale useful for long-range regional ocean planning, which is the portal specialty, by drawing on the real-time data that you can find on the MARACOOS OceansMap. In another example of this, last summer, we worked together to create a series of maps for the portal showing average monthly sea surface temperatures based on 15 years of daily data compiled by MARACOOS. Today, I'm happy to welcome Mike Crowley, the Technical Director of MARACOOS and the Rutgers University Center for Ocean Observing Leadership, and Kelly Nee, Executive Director of Ocean Science for RPS North America, and a longtime collaborator on many portal projects. Mike and Kelly will discuss and demonstrate the maps on the portal and the source products from MARACOOS OceansMap that were used to create them. Just a couple of quick notes before we get going. This webinar is being recorded for the benefit of those who couldn't be here today. Usually I'll have these posted online within a day or two, and you can find them on the portal blog or on the webinar page, where we have a full archive of many past webinars. You're free to type questions into the chat at any time. There will be a Q&A at the end where we'll open it up for discussion on anything you see, but certainly if there is something that comes up you have a question about right away, you are welcome to type that into the screen, and we'll take it as soon as we can. And then finally, I know that there may be some people on the line who are new to the portal. So before I turn it over to Mike and Kelly, I'd like to just quickly provide some background on the site. The ocean is a busy place, and that's especially true up here in the Mid-Atlantic, where we have New York, which is the busiest port on the East Coast, one of the busiest in the world. And that means cargo traffic, tug and tow traffic, and all kinds of marine traffic coming in and out of that area and along the Jersey Shore and Long Island. We have a very busy commercial fishing community out here. We have basically the apex of undersea cable activity coming in and out of the New York, New Jersey area for communications overseas. We have recreational boating. We have offshore wind coming in the future. And what the portal does is illustrate all of these different things so people can see how they relate with one another, and in some cases how they conflict with each other, so that people who are in management roles and stakeholders who are interested in all this can, help make better decisions. The portal currently has over 5,000 different map layers organized under 11 different categories or themes. You can turn any of these maps on one at a time or in combinations with each other to really show just thousands and thousands of different stories. We have a host of different instructional and educational resources for users and tools to help people share maps and collaborate in groups to work on projects in their workplaces and for their interests. The portal team is currently the Monmouth University Urban Coast Institute, where I sit, Rutgers University Center for Remote Sensing and Spatial Analysis, the Nature Conservancy, and our developer EcoTrust out in Portland, Oregon, and we work under the guidance of MARCO, the Mid-Atlantic Regional Council on the Ocean. For those who aren't familiar with MARCO, it is a governor's agreement established back in 2009 by the 5 states from New York down through Virginia to work on ocean issues. And it's currently chaired by the state of New York. One of the things that the portal did was take a lot of data that was scattered in a whole bunch of different places, different government agencies, and bring it under one umbrella. Really just the information that has the most direct relevance to users in the mid-Atlantic states. And so we ingest a lot of data from the federal level portal, which is the Marine Cadastre. We have literally created and shared in partnership thousands of different map products with our partners in New England and ROC and the Northeast portal. And we also deliver a lot of information to the state portals, and in some cases show some of the data that was created from these different state portals on our own site. But what's new here is we've recently started creating map products based on the real-time observational data that you can find on the MARACOOS OceansMap. And that's what we're here to talk about today and see. So with that, I'll turn it over to Mike and Kelly. 1 second while I close out.
All right, am I sharing?
You're good.
All right, good morning, everybody. As Karl said, I'm Mike Crowley, Technical Director of MARACOOS. So Kelly and I are going to be splitting the demo today. I'm going to open up and just talk a little bit about what MARACOOS is, who we are, what kind of data we deal with, and the information. Give you a little background first, and then Kelly is going to get into a demo of OceansMap and show you she's got the cool stuff to show today. So I'm going to give you guys a couple slides, what we do and history, and she gets to show you all the neat things. So without further ado, here we go. And then I also have co-authors here, Mary Ford and Gerhard Kuska, Executive Director and Director of Engagement for MARACOOS. We are a big entity of many, many different groups, and there's a lot of authors here. We probably could have listed, gosh, 20 or 30 different people in here. But to keep it simple, we're just going to put the 4 of us in there to start with. All right, so U.S. ICE. So there is a global ocean alliance, GOOS, Global Ocean Observing System, that does ocean observing all over the world. Even down in Antarctica, in the Southern Ocean, and north, there's all over the world. So U.S. ICE, the Integrated Ocean Observing System, is the U.S. component of this big international system. And then U.S. ICE is further broken down into smaller regions. So here's the map here. There's 11 what we call regional associations that focus on geographical areas of the United States and in the Caribbean that's centered in Puerto Rico. But there's 11 different groups, and we're MARACOOS here in the Mid-Atlantic. And each region is funded directly through NOAA. So the money comes from NOAA to fund all the different groups. But there are 17 federal agencies that are part of ICE. NOAA is the lead, but there are multiple different partners involved in this U.S. ICE to do ocean observing around the entire country. The regions are broken up this way because every different group and every different location, they have a different focal area. For instance, Mid-Atlantic, hurricanes are pretty important if you're in MARACOOS, Socorro, the Gulf of Mexico, the GCOOS area, down in here in the Caribbean, but they're not if you're on the West Coast. Also, if you're studying red tides, certainly the West Florida Shelf, the Great Lakes are areas where red tides are major, major problems. I know the oyster industry up in Washington State. They're becoming an issue in the Chesapeake, but they're not a big focus area for us just yet. So each region does its own regional focus and regional of regional importance to them. So here's the map of our region. So there are 10 states. We're a little more complicated than most of the other groups because there are 10 states. For instance, there's the Alaska Ocean Observing System, that is Alaska. Now, I'm not saying it's not complicated. It's a gigantic area, much larger coverage, but it is one state. So it sometimes becomes a little challenging to try to deal with 10 different states and 1/4 of the U.S. population. One other piece here, I have the certified sticker in the bottom right-hand corner. As of about, I think, a year and a half ago, all of the different groups, all the different, again, the regional associations within IUS, and we're MARACOOS, Mid-Atlantic Piece, we all got certified for our data and the way that we operate, meaning that our data is protected under federal law. It's guaranteed, basically. Did I stop sharing?
You did.
Okay, not sure what happened. I think I had a wireless strap on. All right, we're back.
There you go. You're back.
All right. So our data is certified. So anything that comes through us and anything that that you're going to see on the portal, either data generated by us has to go through a whole set of QA/QC procedures, quality control procedures, or data that's put into our map is either from the federal agencies or through groups that we've applied QA/QC, strict QA/QC procedures on. The data has to be accurate. So that's a very, very important thing. Certification took, boy, I guess over the course of the process, it was over a year to make sure that we could get certified and make sure our data was up to spec and we were going through all the right processes. So this data is federally guaranteed. We have 5 different themes that we focused on. First, maritime safety. We've gone back and we've done work with the Coast Guard. We'll be showing you some data that we've used from HF radar systems that look at surface currents. But we've been helping the Coast Guard with search and rescue going back. Boy, I think it's going back to even when we were, before we were called MARACOOS, going back maybe 15 years or so. So we've been doing a lot of work with the Coast Guard over the years. Fisheries, and we've been working, and one of our big challenges has been convincing some of the marine spatial planning, right, groups, that fish do move and the bottoms change and those sorts of things. So it's seeing that the fisheries do move and fish are moving as the climate changes. Water quality is something we have been also has been a big focus, certainly in the coastal areas, beaches, whether it's hypoxia has been a big one for years that we focused on, especially in the late August, September regions that hits our area. With, I guess, the 1976 event being the most famous anoxic event. But Chesapeake Bay, Vibrio, HABs, those sorts of things. And then in the coastal hazards arena, hurricanes became a big focus. And there's other things. I'm just giving you examples. But certainly with Irene and Sandy, and there's the picture on that bottom center of damage from Sandy. Hurricanes became a really big focus and what impact that the oceans had on hurricane forecasts, and that's been a big focus. And then as we look to the future, we have the energy little button down here. There, as you all probably know, there's a lot of focus now on wind turbine installs, and that's going to be a big impact for all of us doing anything in the Mid-Atlantic. The last number I have from my friends from that are focused on this work is that the agencies would like to see from basically Cape Cod down to Cape Hatteras about 3,000, I think we're 28 or 2,900 installations of turbines between now and 2035. So that's 3,000. So that is going to have a major impact on maritime safety, potentially coastal hazards. But one cool thing, one major opportunity here, other than clearly the energy impact, is the potential to outfit a lot of these with instrumentation. And there's a project going on right now where before they start installing these turbines off of New Jersey, they're interested to learn a little bit more about whale migrations. So they're going to be paying for gliders to go out with sensors on board to listen for whale sounds that will be able to immediately surface, call back and tell them what type of whale is in the area by the sounds it makes. And that's a project funded by Ørsted, and the hope is that that beta project that exists right now becomes an entire mid-Atlantic project while they're doing turbine installations over the next 15 years. So the data sets that we deal with, so starting from, I guess, highest to lowest, satellites on the high end, and we'll talk a little bit about those today. This is the sea surface temperature image in the top left, the Gulf Stream in red, nice warm water. Let's go back. So that's at the high level. We also get data from ocean color from MODIS sensors, and even salinity is something we started looking at. Next level down at the ocean surface, these HF radar currents, and I'll talk more about these. We have an HF radar array that gets data on surface currents every hour throughout the mid-Atlantic. And then also at the surface, these are the national and the National Weather Service and others weather stations data that we incorporate into the work that we do. There's also a series of different buoys throughout the Chesapeake, for instance, that data gets incorporated from. And then drifters from the fishery surface in the Northeast. They do a lot of those drifter deployments that we look at data from. And then gliders, and this is something that MARACOOS is funded to do deployments of. So the gliders, the satellites, and the radar are data sets that MARACOOS goes out, acquires, and then makes available. Yes, satellites are made available by many groups. We do our own local regional products. So I'm going to talk a little bit next about the data that we gather ourselves, which are the satellites, the radar, and the gliders. And then the important thing to note is all of this data gets put into ocean forecast models. Right here in the middle, what you see in the middle here is a forecast model of both ocean temperature and currents. And the ultimate goal is to improve the ocean forecast models. If we improve those ocean forecast models, we improve our weather models. So, data highlights. Satellites. So here's a shot from OceansMap, and there's a sea surface temperature image. People are, I think, pretty used to seeing the Gulf Stream going off of our coast, offshore over here. Colder to the north, the purple colors are colder. Warmer in the Gulf of Mexico. There's the loop current down here in the Gulf of Mexico. Black lines happen to be glider tracks. I'll talk more about those in a minute. So what we focused on for years, and I mean, geez, I think we started putting data online 25 years ago, from the NOLA polar orbiters, otherwise known as AVHRR. Those are the standard data sets that we've been dealing with for a long time. MODIS are satellites that have ocean temperature. They also do ocean color, so they can see phytoplankton. And there's a host of different other satellites as well. Some different products that we do over here with anomalies, water mass tagging. Matt Oliver out of the University of Delaware is leading that effort. I'm getting too happy with my mouse here, clicking too soon, sorry. The one I wanted to highlight real quick was GOES-R, otherwise known as GOES-East. It's the new satellite that's, I think it's actually centered right through Cape May as far as the longitude goes and over the equator. That satellite is giving us temperatures now of the ocean surface every hour, even more. I think we can get every down to half hour or so. That has a hell of a lot of potential because these satellites can't see through clouds. And if clouds are moving, right, clouds move pretty fast. Ocean currents do not. So these clouds move through, they give us windows into what the ocean temperatures are. And if you're getting a GOES image from a geostationary satellite every 30 minutes, rather than one shot every 4 to 5 hours from an AVHRR satellite, you can get a lot of fill-in of data. So this data set is something we're working on now. It has a slight bias in temperature error, and we're real picky about what we put online. Remember I said certified, we have to be very careful about what we put online. So before we get that GOES data up there, we're going to make sure it's good. But boy, that is going to be one hell of a data set, and it's the entire side of the hemisphere. And the fact that it sets over the nadir is the equator, but it's right centered over New Jersey, coming through Cape May. But we have very good resolution of this data set coming through us. So that is going to be something we look forward to, I think, trying to get online in the fall when we're real happy with the quality of that data set. So I mentioned satellites. A lot of people put out satellite data. This is a standard product you're seeing on the left. So, why locally processed products? So this is a standard data product that's made available to modelers around the world for doing atmospheric weather modeling and ocean modeling. It's a standard product that's been around for a long time. The problem is that the way they put these data sets together, they tend to average out real data. So real temporal short-term blasts of different cold water or hot water can be lost. So this is a product on a given day, I think July 8th of 2013. This is the same data set coming from us, a little higher resolution, but you maintain, there's an upwelling center along the coastline. We've got a little gap here, the upwelling center along the coastline, so you're getting that cold water that gets into the models and gives you a more realistic idea of what's happening out there in the ocean. It's lost in this general national satellite product. So we like to keep these localized products so we get a more realistic, high-resolution view of what's going on in our ocean. All right, the radar. So this is one I'm sure that's new to many of you. We'll start with this left image. So this, I see it. All right, back.
Almost. There you go.
There we go. All right. So this is a picture of coastal surface currents from our HF radar network. So we have a total of 41 stations, and they look like these pictures right here. They look like these old whip antennas, the old CB antennas.
Mike, we lost you again.
Yeah.
The screen.
Good?
Hang on a second. There you go. Now you're up.
All right. There are antennas, and they're in pairs, a transmitter and a receiver. And for this network that gives you this information, all these colors are little arrows that are on this grid of surface currents. Red are high speed, blue are slower. And these stations are radar stations all along the beach. You see these red dots along the coastline. Each of those has two antennas, a transmit and receive antenna. It transmits radar beams across the ocean, reflects back off the waves, and comes back to the receive antenna. And what we're able to do by putting multiple different radar sites together is give an accurate view of the surface currents of the ocean up to, well, you can see it's up to, in this case, just over the shelf edge. So you can get out to about 100 miles offshore, so it's a pretty good coverage on a good day like this. So there's 38 stations, and before anyone gets worried, yes, I said radar, and sends out beams across the ocean. If you don't get nervous around your 100-watt light bulb in your house, you shouldn't get nervous around these antennas. They're not like the weather radars that you would not want to sit on top of one of those while they're firing their beams out. These are much lower wattage and harmless to people. And they're nestled at different beaches across, right? You can see down here starting at Cape Hatteras, going north, up all the way to Cape Cod. So we call this our long-range network, getting well offshore. There's also a mid-range network that's off of New Jersey here, this image up here. And there's 7 of these that are located on the Jersey shore. And you can see they're much shorter distance offshore, but they're getting us surface current information offshore. Then we have our short-range systems. I think they actually call them the standard. And you'll see we have them located at Long Island Sound, New York Harbor, Delaware Bay, off of Nantucket, Martha's Vineyard, Block Island, Chesapeake Bay, at the different bay entrances. So we can see the high-resolution dynamics. So when I say high-resolution, these give you information every kilometer. The ones off New Jersey give you information every 2.5 kilometers or so. And the ones that are the long range give you information every 6 kilometers or so. And this data comes in every hour. So this data set is actually one that we pulled into the MARCO portal. And just to show you what some of the data looks like, this is a nor'easter from 2018, Winter Storm Avery. This is the HF radar coverage. You can actually see the arrows of the surface currents circulating around the low pressure system as it moved offshore here. And we've actually been able to give some of this data to the National Weather Service because they're actually able to look at this after the fact and go, okay, you can actually see where the center of the low pressure was at a given hour. Where they do estimates when these things are offshore, we can actually see the rotation in the center of the low. So it's kind of a neat story here. And this isn't a one-time freak thing. We see this all the time with nor'easters that come up along the shoreline, or hurricanes as well. You see the rotation of the surface currents around the center of the low. Just kind of a neat example of what we see in the radar. One cool thing I didn't mention is those systems that we are using off of New Jersey, we're using now to look at wave height. We're actually able to measure the wave heights, not just the surface currents. And that's something that we're working to expand on as we move into the future. There we go. That was my reminder. Okay. All right. Gliders. Not sure how many of you are familiar with the underwater gliders. These are remotely controlled vehicles. They do not have a propeller. They glide through the ocean. They're the same buoyancy as the water they're put into. There's a little hole in the tip of the glider that sucks in about a cup of water, maybe a little more. And that little bit of water coming into the glider makes it dense enough to sink, or when it's pushed out, light enough to rise. And it doesn't just go straight up and down when it sinks and rises. The wings actually propel it forward. So it goes very slowly, maybe a kilometer and a half an hour, and slowly goes through the ocean, top to bottom, getting information. We had about 7,000 kilometers flown in the mid-Atlantic last year. And these are just some maps of those glider locations from the last year, partners in MARACOOS. And the data they get, these are cross-sections. So we have just a cross-section, and this one was in shallow water on the shelf. So as we look at the temperature cross-section going offshore, and then it hits the continental shelf edge. The black is the ocean floor, and you see the ocean floor drop out. It goes offshore, off the continental shelf, and then comes back in a little bit to the shelf edge, goes back offshore, and then comes back into the shallow. You can see it's warm at the surface. There's a little colder water here. This is an image from May, early May. So we're having a little spring warming at the surface, but you can see the water down below is all still cold. And then once you get further offshore, you get the Gulf Stream water and ring dense. So it's warmer, but it's dense, so it stays low. Down here, we have the salinity matchup with the same temperature data set. And the salinity, blue is fresher water, red is more dense, more salty. So it's that warm water is warmer, but it doesn't rise again because it's much denser and heavier than the colder pressure water above it. So these are temperature and salinity. We also do oxygen, optics. We can look at plankton and all sorts of sediment. We have a new sensor that is active acoustics that looks at zooplankton and different frequencies and different sizes. We can do current measurements, waves. pH is new as well. And then passive acoustics for listening for fish tags. And the project I mentioned a little while ago is the wind turbine guys are interested, that's Ørsted are interested in whale detection. So that's a new one, a glider that we hope to get in for the first time in May. Whoop. So demo. So I'm going to sneak out and just really quickly show you guys. Hopefully I'm still sharing. This is the Marco portal. Everyone see it?
Yep, you're good.
All right, Marco portal. And the two data sets that we took out of everything I showed you were climatologies for radar and SST. So, and I want to thank John Bogner, who I believe is online. I think I saw him earlier. John, thank you. Metadata man, making sure I'm doing what I'm supposed to be doing. Thank you. John and I go way back to undergrad together, working at Rutgers. So, John, thanks for helping, and well, not helping, doing it, getting the information all in. Oops, so I'm going to load from scratch. So going to the portal, view the map, start from scratch. Over here to the left, there's a little tab for oceanography, and you can see oceanography data sets. So I'm going to start with the SSTs, so the Mid-Atlantic sea surface temperatures. So these are sea surface temperature data, like I showed you, but what I was showing you were single images from single minutes in time. What you're seeing here are monthly averages over the course of 10 years that were put together. So these are, I'm going to get it loaded. I don't know how this is working. Got a lot of internet being used in my house right now, so pardon me if this is a slow animation. Maybe I'll shrink it down a little bit. There we go. So you see the temperatures changing. Over here, there's a slide bar. We started in January. We're now in September, October, November, December, cooling down. January, February is the coldest. We start to warm up a little bit in March. So these are monthly averages over the course of the last 10 years that you're seeing. And you can see the Gulf Stream here stays pretty stable in red. And then and you see the big changes up on the shelf of the temperature. So that's the one data set that we got in. And now I'm going to pause that. We'll take that off. Now I'm going to show you the radar currents. So we have, these were done not monthly, but quarterly, so by season. So we have, this is winter surface currents averages over the course of the last 10 years as well. So I'm going to zoom in, and you'll see that they're higher resolution. You see how far offshore that these arrows go. And you're able to see that the red are higher currents, the blues are lower, lower speeds, but somewhere in the 10 to 20 centimeters a second range for the most part that we see throughout the Mid-Atlantic. Again, this is a seasonal average in winter, and now I'll put spring. And in summer, just so you see that they're there. And it covers the Mid-Atlantic region, the whole Mid-Atlantic region. So that's a little demo of what MARACOOS does, the types of data that we get. Again, thanks John for getting these data sets in, and again, the metadata is a very important piece of this, letting people know what these data sets are. So now I'm going to hand off to Kelly Nee to show you a little bit about what our data looks like in OceansMap.
Thanks, Mike. Hi, everybody. Good morning. This is Kelly Nee. I'm with the RPS Ocean Science Division, and we work on the MARACOOS Data Management team. And I should be sharing my screen. You should see OceansMap up there now.
Yes.
Okay, great. So what you see right now should look pretty familiar to what Mike just showed you. We're pulling in exactly the same data that we provide out to MARCO for their portal into our MARACOOS OceansMap portal. The OceansMap portal is used to enhance the discoverability and accessibility of all of the data products that are available from MARACOOS. And it also provides visualization and some basic analysis of the data that we have available. And I'll show some demonstrations of that in a few minutes. The layers are organized into this table of contents, and they're organized by category. So you see the HFR climatology showing up under spatial observation. So these are our gridded observation products. This includes all the HF radar data as well as all the satellite data. We also have a number of forecasts included in OceansMap. So those show up under these different prediction categories. So you can look at wave predictions, water level predictions, current predictions, etc. And then we've got a bunch of in-situ observations up here at the top. So these are pulling in observed data from federal sources, from regional sources, and even from some citizen science sources. You can see we've got some of the Surfrider beach water quality data in here too. And I should say on the prediction front, we're also pulling in, we have this current prediction category here, We're pulling in federal operational forecast models, so you can see some of the NOAA sources in here. So we've got operational forecasts for Chesapeake Bay and for Delaware Bay. But we're also pulling in regional sources, so some MARACOOS sources, some SICORA sources, which is the regional association to our south, some NERACOOS sources, which is the regional association to our north, as well as some other various academic sources. So there's a whole smattering of different data types included in OceansMap. You can also use there's a lot of data in here. You can use this filter window to search the data sets if you're looking for something in particular. So you can see sort of my most recent searches in here. And that will filter down the table of contents and show you only what's related to what you searched for. You can also access the data directly from OceansMap. So if I mouse over this seasonal climatology layer that we've been talking about, click on this little info button, I get the abstract for the data, so a little bit of information, background information about it. But I can also click directly over to this Open.Data Access form, so I can make a request to download the data directly from here. And we provide similar links for most of the data sets that are available in OceansMap. Mike showed you a little bit of how to animate data in the MARCO portal. And there's a number of time sliders available for animating data in the MARCO portal, which I'm sure most of you are familiar with. OceansMap works a little bit differently in terms of how things are synced in time. We sync the entire map to a single time step. And because most of our data is time varying, with the exception of some of this climatology type data. So there's one time slider down here at the bottom of the map. It's always here, it's always on, and the data that you're looking at on the map is always synced to the current time step. You can change your time range or your time step using this little calendar control over here. By default, the current time step is set to the equivalent of now, so whatever the time is when you load OceansMap, and the time range is set to plus or minus 2 days. So 2 days in the future because we have a lot of forecast data in here, and 2 days in the past. But you can change that time range to any number of things with these quick links, or define a custom range if you're interested in looking at the data associated with a specific event that happened in the past. So I'm going to go ahead and turn off this climatology layer, and we're going to look at some more time varying data. So I'm going to go and turn on the MARACOOS HFR product. So these are the real-time currents coming in. This was about an hour ago when I loaded my map. I'm going to just zoom in a little bit here so we can see them a little better. I'm going to go back in time a little bit so we can animate them. So I'll go back to yesterday evening and then just hit that play button. Hopefully my internet connection is sufficient that you're seeing that animation come through on your side. So that's just showing an animation of the currents every hour. And these are the observed currents from the HF radar system. So from here, I'm going to turn on a current prediction. We'll go down to our current predictions category, and we'll pick the MARACOOS Doppio model here. And so now I've got two different current data sets, one observed, one predicted, overlaid on top of each other. I know it looks a little confusing, but the cool thing about this is now you can click on the map and create a virtual buoy. And that's going to give us a time series of data from both of those sources so that we can compare how the observations and the model predictions look together. So you can see that there's pretty good agreement between what the MARACOOS Doppio model is predicting and what the HF radar system is measuring, which is pretty neat. So from there, we're going to go in and look at a few more predictions. So I'm going to go ahead and turn off those observed HF radar currents. And I'm going to go ahead and turn on the water temperature prediction from Doppio. So now we're looking at two different parameters forecast from the same model. So this is surface water temperature overlaid with the surface currents, both predicted by the Doppio model run by MARACOOS. So you can see as I turn on that water temperature layer, my virtual buoy stayed on my map, and it added the time series of surface water temperatures to my time series plot down here. A little more information about this plot. So you can see that there's two colors. There's sort of this gray background and then this yellow background. The gray background represents time steps in the past, and the yellow background represents time steps in the future. So your observation data is never going to go past this line here, this differentiate between the gray and the yellow background. And then this blue vertical line right here represents where my time slider is set to. So I can see, I can sync up what I'm looking at in the time series with what I'm looking at on the map. And I can also animate both of these layers together. So go ahead and close this time series to give us a little more map space and just run this animation through again. So now we're looking at an animation of surface water currents and surface water temperature from the Doppio forecast model. And that's all synced in time, right? So we're looking at the same exact time step for the surface water temperature and the surface water currents. Any other layer that I turned on would also be synced to that same time step. So from here, I'm going to go ahead and get rid of the currents. We're going to take a little bit of a deeper dive into temperature. So as I said, we're bringing in a whole smattering of different data sources. So the Doppio model is a regional model. We've also got a couple of operational models that are providing out temperature data. So I'm going to go ahead and turn on the Chesapeake Bay forecast model. Move down here, Chesapeake Bay. So this is a model known as seabox, or the Chesapeake Bay Operational Forecast System, run by NOAA National Ocean Service co-op. And I have to apologize. The seabox model is one of the first models that we pulled into OceansMap, and we haven't updated the color scale that we used to draw it. So the color scales for Doppio and seabox are a little bit out of sync. I did want to show it to you anyway because seabox is a 3D model, and we pull in the full 3D model forecast. So if I create a virtual buoy in the seabox domain, it's going to pull back that time series data that I've showed you already. But you can see because it's a 3D model, I also automatically get this neat profile at that virtual buoy location. So I can see exactly what's going on with water temperature through the entire water column. I'm going to go ahead and close that out. Mike talked to you a little bit about the fact that glider data is so important to the Mid-Atlantic and so important to MARACOOS. And we pull that data right into OceansMap. So I can go ahead and turn on glider track in OceansMap. And we're very lucky that there's one glider that's been out there since mid-March. So this is spray glider SP69. It's been out there since March 19th, and I can tell that by mousing over the glider track. And if I click on that glider track, I can look at water temperature data and entirely, oops, I missed it. There we go. I can look at water temperature data in an entirely different way. So we've looked at a time series of water temperature data. We've looked at a vertical profile of water temperature data at a single point. And now we're looking at a profile of the data that's generated by the glider. So you can see it's moving along in time, how the water temperature is changing based on depth and location. And you can see very clearly the Gulf Stream right here in the middle of this plot. And the warm water that's going from top to bottom of the water column, so all the way down to 3,000 meters of depth or so, which is pretty neat. So I'm going to do one more quick demo for you. I'm going to get rid of all this stuff by turning everything off at once. And I was saying to Mike yesterday as we were talking about this demo, it's pretty rare that we're lucky enough to have had some cool weather to talk about, kind of sync up with giving a demo like this, but I'm sure most of you are aware we had some pretty high winds yesterday, some heavy rains, and so we're going to go ahead and take a look at some of the winds that we had yesterday. So I'm going to go ahead and turn on GFS, which is our global wind model. And we display the GFS data as what we call stream flows. So these animations show what the wind looks like at a single time step. I'm going to go ahead and move back to yesterday, mid-afternoon, so we can take a look at what's going on. A second to refresh, so we can see those very, very high winds that were impacting the entire mid-Atlantic and northeast coast yesterday. And I sit up here in Rhode Island, and you can see things got pretty crazy up there. So that's pretty neat. Let me zoom out a click here. Kind of get a bigger picture of what was going on. You can see this big system offshore here. And from there, what comes along with winds is often high waves. So we're going to go ahead and turn on a wave prediction. So this is the Atlantic WaveWatch 3 prediction. So this is a regional model that's run. It's pretty high resolution and it covers a large area. So it takes a few seconds to load, so please just bear with me for a second as that loads. It's worth it, I promise. There we go. So we set the default drawing of this layer to 0 to 3 meters because under normal conditions, that's sufficient to give us some nice differentiation of what's happening with wave height. Clearly not sufficient for what was going on yesterday. So if we click on this little tools cog next to the layer name, we can change our color scale range. So we'll set the maximum up to 6 meters so we can see where those waves got really crazy. And you can see where those high waves were impacting yesterday. So you can click anywhere in here to look at a time series of those waves and the associated winds. So you can see where those sort of peaked out yesterday afternoon. The other thing you can do is compare the forecast with observations. So if we turn on the seated buoys, so these are buoys that measure wave data specifically, we'll turn on this Barnegat, New Jersey station, or click on this Barnegat, New Jersey station. So now we're looking at the measured wave information at this particular buoy, but we can also pull in the forecast or the predicted wave. So we can go ahead and turn on that forecast time series. Let's get rid of the direction. There we go. So now we're looking at how the predicted waves compare to the observed waves from the event that we saw yesterday at this station offshore New Jersey. And you can dive one step deeper if you want to compare models to observations and use the OceansMap Validate tool. So from here, I can go over to my Tools menu and click on that Validate tool. I'm going to tell it that I want to compare wave heights. I'm going to select that Barnegat station, which I can search for based on name or station number. And then I'm going to go ahead and select that same model prediction that we were looking at. And so this is calculating a comparison between the Atlantic WaveWatch 3 regional forecast and that CDIP station on the fly. So none of this is cached or pre-calculated. So it's showing you that time series comparison again, but it's also bringing back a number of error statistics. So you can start taking a closer look at how well the various models available from MARACOOS are doing against observations. So we could easily switch up the model we're looking at here. So go from, say, the regional WaveWatch 3 to maybe a local national weather service model. So this is a nearshore wave prediction system. And we can see it's a bit of a higher resolution model in terms of how frequent the time steps are. The R squared and errors are about the same. So it's a pretty neat way to compare between different models. You can also do the comparison over different time periods. So by default, we're looking at the last 7 days. But we can also, look at the last 30 days. If we're patient, we can look at the last year and really dig into how well these models are doing against observations at various points. So from here, I'm just going to switch back to our map view and point out a couple of other features about OceansMap. With some basic stuff, you can access the legends by clicking on this Legends tab. That'll show you a little bit more about what the various colors mean. You can change your base map to any number of backgrounds. In this base map, in this backgrounds tab, you can set your unit system. So if you're interested in looking at English versus metrics units, you can do that here. You can also create a permalink. So this is a way to share your map, essentially. If you copy this link and share it with somebody else, it will allow them to see exactly what you're seeing on your screen and kind of give you a way to save what you've been looking at. So that's about everything that I wanted to show. Be happy to turn it back over to Karl and take any questions.
Great. So we'll now open it up to questions from the audience on anything that you've seen, heard regarding the Ocean Data Portal or OceansMap. Feel free to just type them into the chat and I'll read them aloud so people who are viewing this recording later can hear them. So I'll start off with one. Mike, I wonder, as far as the surface currents maps that we see on the Ocean Data Portal, to what extent are they reflecting wind patterns? What are the other drivers and the extent to which they matter in terms of what we see?
Can we give Hugh Rorty, can we allow him to speak? Sorry to put you on the spot, Hugh, or no?
Only if he's
Yeah, I'm on the phone. Can you hear me?
Yes.
Yeah.
Hi, everyone. Yeah, so my name is Hugh Rorty. I'm the manager for the Mid-Atlantic HF Radar Network. And so just in response to the question, probably the wind is a dominant factor in the currents that we see. Probably maybe 50 to 75% of the energy that we see in the surface currents are derived from the winds. And then probably 20 to 40% is due to the tides. And then a small percentage is due to any background flow that's moving through the area.
All right. Thank you for that. We actually have a couple of questions in the queue now. So this first one from Kimberly. When you place a buoy on the map, do you just click on it, or is there something else you need to do? Maybe Kelly can address that one.
Sure, absolutely. Yeah, if you're going to create what we call a virtual buoy, you can just click anywhere on the map. So I'll go ahead and click someplace new. And that created what we call a virtual buoy. You can see that little white dot that's flashing a little bit. That's where I clicked. And this is the data at the location that I clicked for the current time that you see over here on the left, and then the time series at that location in the plot there. If you want to click on an actual buoy location in order to sync up observation and model data, then you just click on that actual buoy. And you can kind of tell that you're about to click on a buoy because when you mouse over them, you see the tooltip with the station name.
Mm-hmm. So we have another question that's pretty closely related, and that's, can you download the virtual buoy data, plot, or the graph directly from the OceansMap?
You sure can, and my apologies, I should have pointed that out. There's this little download button right here on the plot, and you can download the data as, it's not popping up. Normally you can download the data as a CSV or a MATLAB file or NetCDF, and you can also download the plot image.
Who else has questions on anything you've seen or heard regarding the portal or OceansMap? Okay, so we've got, it's about 4 minutes to noon, so we've pretty much finished right on time.
Yeah, I see there's a couple questions in the chat session.
Yeah, we already went over them.
Okay.
So unless anybody has any further, give it one more minute here.
Hey, Carl, this is Mary. Do you mind if I say something real quick?
Mm-hmm.
I just want to say, I mean, there's a lot going on with OceansMap, and you were inundated with a lot of MARACOOS information. So if anyone has questions or as you're playing with OceansMap, you forget some of the functionalities Kelly went through, or you're trying to do something and not quite sure how to do it, please just email info@maracoos.org, and we'll make sure the question gets to the right person and get back to you.
That's a great point, and I'll echo that and say that for the Mid-Atlantic Ocean Data Portal, we're always happy to do individual, webinars for your work groups, or even if you have questions about anything that you're wondering about, I can always queue up a share screen call and help you out with that. Normally we would do even in-person trainings, but that's off the table for the moment. But hopefully in the near future we can get back to that. And you can always contact me through the email that's at the bottom of the portal page, which is portal@midatlanticocean.org. Okay, so 11:57. I think we'll call it a morning. This was a really informative discussion, and thank you again for being on this webinar. Mike and Kelly and Hugh and Mary and everybody else who joined us today. Again, we'll have a recording of this posted on the portal very soon. And thank you again for joining us. Have a great day.